So the goal of this video is going to be to derive the Feynman's path integral, right? Now, if you remember from the previous video in this series, um, I described a particular path as an example to you from some source S to O, detector O. Uh, I described some path that was something like this, right? And we said that we approximate this path by some straight line segments. So that was something like this, right? And then we said that we let these segments tend to 0. So for this, I said that we can write down in this Dirac's notation, we can write down the amplitude as QF and use this unitary operator exponential iota h t on qi, right? And this is how we can write down the amplitude for a particle that leaves the source S and arrives at the detector O. Right. Now, one thing I would like to mention before I proceed further is that we are going to be using natural units where I set h bar is equal to 1, right? In all of the rest of the calculation. Right. Now, so let's get to the main point, that is deriving the Feynman's path integral. And I shall begin so by dividing the time t for the particle into n different segments, right? Or in fact, n equal segments, such that each segment would last for some time that would be delta t, and that is t over n. So every segment would last for this t over n, delta t. Now with this, then what I can do is I can write down this amplitude is as being equal to well, qf, and now for every segment I would have this unitary operator as exponential iota Hamiltonian times delta t. So that's for one particular segment, and for all of the segments I would have this factor of exponential. So I would keep multiplying this until I reach the last segment, right? The last straight line segment over here. So that's keep multiplying exponential iota h bar, exponential iota h, where h is the Hamiltonian for your system, times delta t. And then close this with qi, right? Now recall that what is q? This ket q is just the state of the particle, right? So it's just a state of your particle. So what that means is that then this state qi should form a complete set of states. What that means is that this, if I take this integral dq of this outer product of q, it should evaluate to 1. So that's what you call a completeness relation in quantum mechanics. Now, because this is just equal to 1, I can use this and insert this 1 between each of these factors of exponentials, right? So if I do so, I can write then down this whole thing would be equal to now I would have, for every exponential factor, I would have the integral carried out over dq. So I would have to take the product of, say we have n segments, right? So I would have to take this product of integral dq n times. So how do I do that in mathematics? Well, I just apply this thing, this take the product from some j is equal to 1 and take it n times, right, of this integral dqj, right? Because we have to insert this relation for every factor of this exponential. So that means we have to insert it n times, right? Okay, so well, and then I would just have this thing, right, which is well, qf, and now I would have exponential iota h delta t, and then I would insert this thing. So well, it would start with qn minus 1, qn minus 1. Now this is just 1, right? So I can put this down in there. And then again, I would have this exponential iota h delta t. And this time I would have qn minus 2. And this would go on, right? Up until you have your last two states, which are q2 exponential iota h delta t, and here you would have q1, q1, and finally you would have exponential iota h delta t, and your initial state, that was qi, right? So you started with the final and you end with your initial, right? In this particular expression, right? Okay, now you have to pay attention to the individual factor of this thing, that is qj plus 1 exponential iota h delta t and qj, right? So well, it's this thing, right, generalizing this thing. So well, now let's do something that is very simple, right? So what is that? Well, that is, we would compute this thing that I wrote over here for a free theory, right? So well, what is a free theory? A free theory is where you don't have any interaction term. So that means that your v is equal to 0. What that means for your Hamiltonian is that it would just be p hat squared over 2m. Now this hat over here is to remind you that this Hamiltonian is your operator and this p is also an operator. Now uh, remember that the eigenstate of this operator p is written as this ket p, such that when you take your operator p and act it on the eigenstate p, it should give you some eigenvalue, let's call it p, and your same exact state p get, right? Okay, so now also from quantum mechanics or elementary quantum mechanics, recall that this inner product of q and p is just equal to the exponential iota p dot q, right? Now what does this mean? This just tells you that the momentum eigenstate is just a plane wave, or a plane wave solution in your coordinate representation, where again q is just your coordinate. And this is of course with some normalization, which you can write down as the integral of dp over 2 pi, and the outer product of p's is equal to 1. So this is the normalization for this thing. Now with this then, we can simply again insert a complete set of states using this thing in our above equation over here, right? So let's go and do that, right? So what would I have? Let me write this thing down. Q j plus 1 exponential negative iota, and now yeah, of course I'll have delta t Now for the Hamiltonian, I would just put in here p square hat over 2m for a free theory, right? And then we would have qj. Now, what would this thing be equal to? Well, it would simply be equal to using this thing, right? Let's insert this thing in here. So you would have your integral dp over 2 pi, and let's put this, you would have qj plus 1 exponential negative iota delta t p hat squared over 2m, and then you would have your p, and then finally qj, right? So all I have done is I have inserted this thing in this expression over here, right? Okay, so now note that since the momentum operator over here, it is acting on the eigenstate p, we can simply replace it with its eigenvalue, that is just p. So it's just a number now. So if I do that, well, I can then simplify, or well, at least just write this down as dp over 2 pi exponential negative iota delta t, and now replace it with its eigenvalue. So p squared over 2m. See, note that I don't have any hat over here. Now it's just a number and not an operator. And well, over here I would have qj plus 1 p qj. Right. Now I can solve this thing, this complete thing, by using this equation over here. And if I put this equation in this expression over here, I end up with the integral over dp over 2 pi exponential negative iota delta t p squared over 2m times exponential iota p of qj plus 1 minus qj, right? So this is iota p times qj plus 1 minus qj, right? Now this integral over here, it is just known as a Gaussian integral over your momentum p. And if you evaluate this Gaussian integral, it simply gives you negative 2, well, here comes an iota, negative iota 2 pi m over delta t, square root of this, so 1 by 2 exponential iota m qj plus 1 minus qj squared over 2 times delta t, right? Okay, so all I have done is I have evaluated this Gaussian integral, right? So that's just some mathematics, and I hope that you know how to do a Gaussian integral, right? Okay, so from this then, what I have is that my this thing which we were evaluating, qj plus 1 exponential negative iota delta t p hat squared over 2m and qj, this is what we were evaluating, right? So this turns out to be negative iota 2 pi m over delta t square root exponential iota delta t m over 2, and then you have this qj plus 1. Let me write it down a bit neatly. qj plus 1 minus qj and over delta t whole thing squared, right? Okay, so if you go back up here, this thing, this equation that you have over here, let's simply we just evaluated this thing right now, right, which is over here, that is equal to this thing. Let's just take this and put it back in this equation over here, right? Okay, so let's do that. And so what you have is that whole thing then becomes equal, what whole thing, right? This whole expression or this whole equation, right? What is on the left hand side of this equation? It's let me write it down. Well, let's get rid of the sign. On the left hand side we have qf exponential negative iota h t and qi, right? Where again, remember that I'm using the Hamiltonian for a free theory, right? So this thing turns out to be, well, using this expression, we can write it down as negative iota 2 pi m over delta t, and we have square root over here. But if you go back up here in this expression, you have the power raised to n. So because you're adding this factor of exponential n times, so I'll raise this to n power, and then you have root from here, so n by 2, and then you have this product j is equal to 0 to n minus 1, and then you have integral dqj exponential iota delta t times m over 2, and then you have your summation from j is equal to 0 to n minus 1 on this q j plus 1 minus qj over delta t, right? And of course all of this thing is squared, right? So all I have done here is I have taken this thing which I just evaluated to be this thing, and I have substituted in this expression that I have over here, right? Okay, so now if you carefully look at what I have on the right hand side of this equation, my q0 would be the initial state qi, and the last that would be qn is my final state qf, for obvious reasons, right? Okay, so with this now we are ready to go to the continuum limit. Now I know those are some fancy words, right? But it just means that we are going to simply let delta t tend to 0. So once we do that, Newton and Leibniz taught us to simply replace this thing that you have qj plus 1 minus qj over delta t, and this whole thing is squared. We can just replace this by using the differentiation as well as q dot squared, right? So it's just the time derivative of your generalized coordinate. And also we know that we could replace this summation j is equal to 0 to n minus 1 by this integral from 0 to t. Right, now with this, now we can finally define the integral over all the paths as simply to be equal to the integral capital dq of t, where capital dq of t is, well, let me write this down. It is simply equal to limit where I'll take my n to infinity for all, including all of the possible paths, right? Or all the segments actually, because if you go back up here, these were your segments, and we have to take all of these segments to infinite so we can make this continuous line, right? Okay, so let's go back down. You have negative iota 2 pi m. Again, I'm writing this from this expression over here, right? Okay, so negative iota 2 pi m over delta t, and of course power n by 2. And here we have the product carried from j is equal to 0 to n minus 1 of what? Of this integrals dqj. Now the path integral representation of all of this is then, the path integral representation of this thing, which is the amplitude, it was negative iota h t qi, is simply then the integral dq of t times exponential iota 0 to t, the integral is carried out over time, 1 half m q dot squared. Again, I have replaced the summation by this integral and this whole thing by q dot squared in this expression over here, right? Perfect. So, well, this result actually screams out that to obtain this thing over here on the left hand side, all you have to do is integrate over all of the possible paths that are q of t, such that your q of 0 is your initial state qi and q of t is your final state qf. Now, again, note that we have started off with what is called a free theory, where v is equal to 0. Right, so you should, by following the same exact procedure that we did for a free theory, show for yourself that had we not ignored v, or had we not done this thing, setting v is equal to 0, what we would have was q f exponential negative iota h t qi. This thing would simply have been the integral dq of t exponential iota 0 to t integral dt 1 half m q dot squared minus v of q, right? So it's exactly the same as this one with a factor of negative v of q added to this term over here. But now, from this, quickly recall that what is this thing? Well, this thing is simply your Lagrangian, right? So it's L q dot q, right? So because this is the kinetic term and this is the potential term, right? So that's your Lagrangian then. But again, recall that what is this whole thing, which is the integral over dt of your Lagrangian q dot L of q dot and q. Well, it's simply your action, right, from classical mechanics, S of q. Now action is just a functional of the function q, right, where q is your generalized coordinate. So if I use this thing and I put it in this expression that I have over here, what I get is, well, I'll finally have the general path integral representation as qf exponential negative iota ht qi. This amplitude is given by the integral over dq, which is a function of time, exponential iota s of q, where again s of q is just the action. Right, and we are done. So this thing then is your path integral representation of quantum mechanics. Now, this formalism of quantum mechanics is actually a very neat one for not one but a lot of reasons. But one of which is that if you use this path integral representation, you can very easily show the classical limit of quantum mechanics, right? And so for this video, we are done with the main goal of the video was again, or even the main goal of the series was to develop the path integral representation of quantum mechanics. If you would like me to derive and well even explain the classical limit of quantum mechanics from this path integral, um, I could do that in another very short video. But again, it would be simply done by, well, if you remember in the earlier part of the video, I said we would use h bar equal 1. But now we could just replace this in here and we could include h bar over there in this expression. And all we would do is we would take the limit of h bar tend to 0, right, in this whole path integral representation, and we would then easily recover the classical limit of quantum mechanics.